In this video, we are going to be going over logarithmic and exponential equations. So before we get into the examples, there's kind of two important things I want to note. So if we ever have log base a of u equals log base a of v for any expressions u and v, then we can conclude that u is equal to v. So if we have logs with the same base, then we can conclude that the expression inside the logarithms in the equation, or rather the expressions inside the logarithms in the equation, are equal to each other. And if we ever have a to the u equals a to the v, then we can also conclude once again that u is equal to v. And again, this holds for any expressions u and v. So it's not like u and v have to be like a single variable or number or anything like that. They could be entire expressions. So in the following examples, we want to solve each logarithmic equation and express our solutions as an exact answer. So what we're going to do here is we are going to use the properties of logarithms from the previous section to try to get a single logarithm on both sides of our equation. Then we can use the note at the top to conclude that the expressions inside the logarithms, once we have a single logarithm on each side, are equal to each other, and then solve from there. All right, so for our first example, we're given log base 2 of x plus 9 minus log base 2 of x equals log base 2 of x plus 1. So we can go ahead and use the quotient property on the left-hand side here to rewrite this as log base 2 of x plus 9 over x equals log base 2 of x plus 1. Okay, and then now that we have a single logarithm with the same base on each side, we can go ahead and conclude that x plus 9 over x is equal to x plus 1. So let's go ahead and drop the logarithms using the note at the top. And now we're just considering the equation x plus 9 over x equals x plus 1. Okay, and since we had log base 2 of x as one of our terms here, this means that x is going to be greater than 0, so there's no problem with us dividing by x here. And we can go ahead and multiply both sides by x without multiplying by 0. So doing that, we end up with x plus 9 equals x squared plus x. And then continuing to try to solve for x, we can subtract x minus 9 from both sides. Or rather, we can subtract x plus 9 from both sides. So subtract x and subtract 9 from both sides. And we're going to end up with 0 equals x squared minus 9. Because we're going to have x and then minus x. So those guys will cancel out. And we'll just be left with x squared minus 9. And of course, this quadratic has two solutions. X equals -3 and positive 3. But since we're dealing with logarithms here, we wouldn't include the negative solution because it's not going to be in the domain, like -3 is not going to be in the domain of log base 2 of x nor log base 2 of x plus 1 because we would have a negative inside our logarithm there, and we can't have that. So let's put a slash through that solution. We're not going to include that. We're just going to take x equals 3. All right. Next, we have log base 5 of 4x equals log base 5 of x plus 3 plus log base 5 of x minus 1. So again, we can use the properties of logarithms here to go ahead and write what we have on the right-hand side as a single term. So we can use the product property to write this as log base 5 of 4x equals log base 5 of x plus 3 times x minus 1. Okay, and then we can go ahead and use the note at the top to say that this is equal to, or this is the same as the equation 4x equals x plus 3 times x minus 1. And by the way, foiling that out, we're going to end up with x squared, and then we'll have 3x minus x, so plus 2x in total, and then 3 times minus 1 minus 3. Okay, so we have a quadratic, so let's go ahead and get it in standard form by subtracting 4x from both sides, and we're going to end up with 0 equals x squared minus 2x minus 3. And the quadratic on the right-hand side is going to factor as x minus 3 times x plus 1. So this quadratic has two solutions, x equals 3 and x equals -1, but again, we only want the positive solution here because, for instance, we have log base 5 of 4x as one of our terms from our original equation. So -1 wouldn't be in the domain of that logarithm. So we're just going to include the positive solution, x equals 3. All right. Next, we have log base 6 of 2x plus 4 equals 2. So again, we're going to try to get logarithms with the same base on each side. Here, the base is going to be 6. And the way we can do that, so if we notice, we only have just the single number 2 on the right-hand side, but we can use that power property. And so we can think of 2. So let's go ahead. And the first thing we can think is that, well, 2 times 1 is equal to 2. And by the way, 1 is equal to log base 6 of 6. So we can rewrite this equation as being the same as log base 6 of 2x plus 4 is equal to 2, and then times log base 6 of 6. Then from here, we can go ahead and use the power property to say that this is the same as log base 6 of 2x plus 4 is equal to log base 6 of 6 squared. Okay, now we can use the note at the top, since we have logs with the same base, single logarithms with the same base on each side, to go ahead and conclude that what we have inside the logarithms are equal to each other. So we have 2x plus 4 is equal to 6 squared, which, by the way, is going to be 36. So 2x plus 4 is equal to 36. And then solving for x, we'd subtract 4 from both sides. We'd get 2x is equal to 32. And then finally, we'd divide both sides by 2 to get x is equal to 16. Next, we have log of m plus 25 equals 1 plus log of 2m minus 7. Again, since we just have log here, that means the base is 10. So we can go ahead and rewrite this. So we can rewrite the right-hand side as log of 10 because, again, that's going to be equal to 1. So log, the base is 10, so log of 10 is equal to 1. And then plus log of 2m minus 7. And then from here, we can use the product property on the right-hand side. So we have log of m plus 25 equals log of 10 times 2m minus 7. And then we can now use the note at the top to drop the logs and consider the equivalent equation. M plus 25 equals 10 times 2m minus 7, which is the same as 20m minus 70. And so solving for m, we are going to end up with 95 is equal to 19m. And then dividing both sides by 19, we're going to get m is equal to 5. All right, next we have the natural log of x plus 2 minus 4 equals minus the natural log of x minus 2. So there's a few different ways we could think about doing this one. What I think we should do is add natural log of x minus 2 and 4 to both sides first. So we end up with the equivalent equation ln of x plus 2 plus ln of x minus 2. Again, we added natural log of x minus 2 to both sides. And then since we added 4 to both sides, we just have equals 4 on the right-hand side. And then again, like in example 3, what we can do is we can say, okay, 4 is the same as 4 times 1, and 1, by the way, is the same as natural log of e. Again, base of natural log is going to be e. So it's like we have ln of x plus 2 plus ln of x minus 2 equals 4 times ln of e. Okay, and then from here we can use the product property on the left-hand side and the power property on the right-hand side to say that this is the same as ln of x plus 2 times x minus 2, and then is equal to ln of e to the 4. Okay, and then we can go ahead and use the note at the top to drop the logarithms and just consider the corresponding equation where we just look at the arguments inside the logarithm. So x plus 2 times x minus 2 is equal to e to the 4. And by the way, if we multiply out x plus 2 and x minus 2, so this is a difference of squares factorization, if you can't tell. And what we end up with when we FOIL everything out is going to be x squared minus 4. And then equals e to the 4. Okay, and then solving for x, we would add 4 to both sides and take the square root. And again, technically there is a positive and negative solution here when we take the square root, but we only want the positive one. So x is equal to the positive square root of 4 plus e to the 4. And again, we were asked to write our solutions exact, so we're going to leave our answer just like that. Okay, and then in the last of these examples, we have natural log of e to the y minus 2 times natural log of e equals minus natural log of e to the 4. So again, the base of the natural log is going to be e. So we can use the power property here to rewrite ln of e to the y as y times ln of e minus 2 ln of e equals minus 4 times ln of e. And again, since the base of the natural log is e, ln of e is going to be 1. So we have y times 1, so just y, and then minus 2 times 1, so minus 2 equals minus 4 times 1, so just minus 4. So we have y minus 2 equals negative 4, and then adding 2 to both sides, we're going to get y is equal to negative 2. All right, in the next examples, we are going to solve exponential equations. And again, we're asked to express our solutions as exact answers. So for our first example, we're given 2 to the x is equal to 7. And so what we can do is take log base 2 on both sides. In doing that, we're going to have log base 2 of 2 to the x is equal to log base 2 of 7. And then, of course, using the power property is going to allow us to move x from the exponent. So we have x times log base 2 of 2 is equal to log base 2 of 7. And of course, log base 2 of 2 is going to be 1. So we have x is equal to log base 2 of 7. And again, we're asked to leave our solutions in the exact form. So we're going to leave our answer like so. All right, next we have 10 to the 3y minus 9 equals 7. So what we're going to do here is take log base 10 on both sides. So just log of 10 to the 3y minus 9 is equal to log of 7. And then again, we can use the power property to say that log of 10 to the 3y minus 9 is the same as 3y minus 9 times log of 10, which is of course going to be 1. So just 3y minus 9 on the left-hand side is equal to log of 7. And solving for y, we would add 9 to both sides and divide by 3. And we'd end up with y is equal to log of 7 plus 9 divided by 3, which by the way simplifies to log of 7 divided by 3 plus 3. All right. Next, we have 3 times e to the x squared equals 1200. So what we can do here is take the natural log on both sides. But first, let's divide both sides by 3. So dividing both sides by 3, we're going to end up with e to the x squared is equal to 400. And now we can take the natural log on both sides. So ln of e to the x squared is equal to ln of 400. And then we can go ahead and use the power property on the left-hand side to simplify the left-hand side to just x squared equals natural log of 400. And then we can take the square root here on both sides to get that x is equal to plus or minus square root of the natural log of 400. And of course, we can consider both the positive and negative solutions here, because if we think about plugging in plus or minus the square root of ln of 400, well, into our original equation, we would have 3 times e to the plus or minus ln, or plus or minus the square root of natural log of 400 squared. And then, of course, when we square it, we're just going to have e to the natural log of 400. And e to the natural log of 400 is just going to be 400 times 3 is 1200. So both solutions satisfy the equation. All right. And then for the last of these examples involving the exponential equations, we have 5 to the 6x minus 3 equals 2 to the 4x plus 1. So we could either take log base 5 on both sides or log base 2 on both sides. Either way, we will reach our solution. It will just make like the exact form of the solution look slightly different depending on what we do. How about we take log base 5 on both sides? So doing that, we would have log base 5 of 5 to the 6x minus 3 equals log base 5 of 2 to the 4x plus 1. Okay, and then from here we can use the power property to say that the left-hand side is the same as 6x minus 3. And then equals 4x plus 1 times log base 5 of 2. Okay, and then from here we would want to solve for x, so we would distribute log base 5 of 2 over the two terms on the right-hand side. So we'd have 4 times log base 5 of 2 times x. And then we could subtract that from both sides and add 3 to both sides to end up with 6x minus 4 times log base 5 of 2 times x equals 3 plus 1 times log base 5 of 2, or just log base 5 of 2. Okay, and then we can go ahead and divide both sides by 6 minus 4 times log base 5 of 2 to solve for x. So we're going to get x is equal to 3 plus log base 5 of 2 over 6 minus 4 log base 5 of 2. All right, now we have 2 word problems. So for our first word problem, it says that according to projections by the US Census Bureau, the world population in billions is approximated by the function f of x equals 4.834 times 1.011 to the x, where x equals 4 corresponds to the year 1984. So x is just counting the years after 1980. And then we're asked, when will the population reach 7 billion? So again, it says that f of x models the world population in billions. So the value of f of x is already in billions, so we can just set f of x equal to 7 and then solve. So doing that, we end up with the equation 7 is equal to 4.834 times 1.011 to the x, and we want to solve for x. So the first thing that we can do is we can divide both sides by the coefficient 4.834. So we end up with 1.011 to the x is equal to 7 divided by 4.834. Okay, and then just like in the previous examples, we can take log base 1.011 on both sides. So we have log base 1.011 of 1.011 to the x equals log base 1.011 of 7 over 4.834. And by the way, we're just leaving this fraction as is just to keep our answer as exact as possible, so not doing any sort of like intermediate rounding. And then of course the left-hand side is going to simplify to just x according to the power property. So we have x is equal to log of 1.011 or log base 1.011 of 7 over 4.834. Which, by the way, is approximately 33.84. And again, this is years after 1980. So rounding to the nearest year after 1980, the nearest whole year would be 34 years after 1980, which would be 2014. Okay, for our last example, it says in the Central Sierra Nevada mountains of California, the percent of moisture that falls as snow rather than rain is approximated reasonably well by the function p of h, which is equal to 86.3 times the natural log of h minus 680, where p is the percent of moisture as a percentage as snow at an altitude of h feet. With h between 3,000 feet and 8,500 feet. And it asks us at what altitude is 50% of the moisture snow. So what we're going to do here is set p of h equal to 50 and solve. So that gives us the equation 50 is equal to 86.3 times natural log of h minus 680. Okay, and then what we're going to do is add 680 to both sides. So we have 730 is equal to 86.3 times natural log of h. And then we can go ahead and divide both sides by 86.3 to get that the natural log of h is equal to 730 divided by 86.3. And then what we can do from here is raise both sides to the e, because of course e to the ln of h is just going to be h. And then on the right hand side, we'll just have e to the 730 over 86.3. So h is equal to e to the 730 over 86.3, which is going to be approximately 4,716.7 feet.